All right, so we're going to go through the test number 3. And I apologize for not being able to hand them back, obviously, because I'm not on campus today, but I should be back on campus tomorrow. And yeah, we can go from there. All right, first problem. So you have a 50 horsepower, 3-phase, 60 hertz induction machine. And you can see that there are 6 parts or 6, whatever G equates to, kind of quickly. But the key thing is, if you read what's significant, all I really care about to do this problem is, first up, I have to know it's an induction motor. That's kind of important. I have to know, let me switch to this one. So 60 hertz is important because that's a speed characteristic. I know it's an induction motor. And I also know this part right here, which is pretty important to do this. And so if you remember from your torque versus speed characteristics, kind of went like this. And what we said is most of the machines, induction motors, operate at this slip, so 1 to 3% slip, which is very close to synchronous speed. So your mechanical speed is 873. If you look closely at that, what you realize is that your synchronous speed should be relatively close to 873. And we know in 60 hertz, or if you can't remember, you know that the general equation for synchronous speed is going to be equal to 120 times the electrical frequency divided by the number of poles. And since this is an RPM, you would have had to convert that from RPM to radians per second. So remember, this is in revolutions per minute. And then you have to multiply 1 minute and 60 seconds. And then you have 1 radian in 2 pi revolutions. And so what you're left with is radians per second, is the conversion that you would do, right? So this one actually gives you omega sub s. Well, we're given omega sub s. Now what we need to do is calculate what the equivalent of RPM would be. So if we did this calculation and we just started plugging in a certain number of poles, we would see that NS at P equals 2 is equal to 3,600. At 4, it's 1,800. At 6, it's 1,200. At 8, it's 900. And you can continue to go on and on and on, but what you realize is that out of these 4 here, 900 RPM is really close to 873 RPM. So through the process of elimination, P had to be equal to 8, had to be equal to 8 poles. And again, this was a concept or a thought that was based on the actual operation of the machine at full load, which was 873. Once you had the number of poles, you actually didn't even need to calculate, you didn't really need to calculate you didn't need the number of poles to calculate slip, but what you did need to know is that 900 RPM is what would be equivalent to the synchronous speed. So to calculate slip, you could have gone and you could have said slip is equal to the synchronous speed minus the mechanical speed divided by the synchronous speed. And let me know if anybody wants any answers on these or not, but hopefully these are pretty simple calculations you can do on your own. Once you have the slip, then the frequency of the rotor, which is the frequency of the motor, right? Because there's 60 hertz, which is the frequency of the grid. So the only other frequency that you would have would be the frequency in the rotor, is just the slip times your electrical frequency. Now, the speed of the rotor field with respect to the rotor itself, remember the whole concept of an induction machine is we have a magnetic field. So we have our magnetic field. We'll draw that here. We'll call it B sub S. And that has to operate at synchronous speed. We also have a rotor magnetic field, and that too has to operate at synchronous speed. And they both have to operate at synchronous speed because we want to output a constant torque. We want to make sure that our torque stays constant. The rotor itself operates at N sub M. And all of this is relative to a stationary object. So drawing this figure, what you can see is that the rotor field is spinning at synchronous speed. The rotor is spinning at mechanical speed. So the actual, is there a question? Hello? All right, if there's no question, I'll continue on. So what I see is that the rotor field is spinning at n sub s, but my reference point, that's what with respect to is n sub n. So I can pretend that I'm standing on this rotor spinning along at n sub n. And what I see is something spinning on at n sub s. So the reference is ns minus n. That's the actual speed relative to the rotor. So you're just taking your synchronous speed, the actual speed of the rotor field, and you're pulling out your reference, which is your mechanical speed, and that's how fast it's rotating. Then the next one is the rotor field with respect to a stationary object. That's easy. That's n sub s. The rotor field and the stator field with respect to the stator field. So now what I do is I move my person here, and I'm moving along at synchronous speed. So the speed difference is ns minus ns. Has to be equal to 0. And then the shaft torque at full load. So this is pretty easy. Power equals torque times omega. So you have to solve this equation for torque. Power divided by omega, and this is omega sub m. So I need to take my power and multiply that by 746 watts per horsepower, because the power is in horsepower. And then I have to convert 873, which is an RPM, and convert that to radians per second. All right, so a lot of people just did 25 divided by 873, which is a pretty, I don't know what that unit would be. That's some unit that doesn't really have a lot of representation in anything physical. So that would not be something you would see. Questions on number 1? Any questions? Hard, easy, fair, not fair? Not sure what to think. It's really quiet. So should I continue on or should I pause?
I'm good to go.
Okay, well, hearing nothing else, let's move on to number 2. So again, a lot of these problems are, you have to look at what's relevant and what's relevant. So to calculate air gap power, I don't actually need to know. Oops, the chat. All right, thank you. I missed that part. So looking at this particular problem, because I know the current at a power factor and I know the voltage, what I can do is I can actually immediately start to calculate, how does this particular machine do its losses? So I don't have any equivalent circuit parameters, so I can't calculate I1 and I2 and do the calculation there, but I still need to calculate air gap power. So the only thing I can do is draw my diagram, which has a Pn equals square root of 3 times V line. So I'm going to put V line here and I line. The first power I'm going to drop off is my stator copper loss. The next power I'm going to drop off is my core losses. Then I'm going to drop off my rotor copper losses. Continuing on. Well, and let me do this. And at this point, what I do is my power now starts to get defined here. So the power here, from this point over, this is the power that is jumping across the air gap. Once I get my power losses from my rotor copper losses, this is power that is converted to mechanical power. Now I have to take out any mechanical losses, which in this case is P, friction, and windage. And at this point now, all the power out is available for mechanical. So this is P out, and that's equal to, torque out times omega sub E. So the air gap power, you can see from this diagram, P air gap is equal to P in minus P stator copper loss minus P core. Okay. So then my mechanical power developed is here. So this is the mechanical power. This is the equivalent to T developed. Oops, sorry, it's a little hard to read. So this is T developed times omega sub m. So my mechanical power developed is going to be determined by taking my air gap power and subtracting out my converted power. So P air gap minus my rotor copper loss. That's going to be equal to P converted. And from here, I can go ahead and calculate my mechanical power, which is, well, actually, I don't even need to calculate mechanical torque because this is just mechanical power. So all I needed was the current converted power, which is P air gap minus P rotor copper loss. So I don't even need to calculate torque as of yet. My next step is what is the shaft output power in horsepower? So I'm already over here to converted. Now I just have to get rid of friction and windage. So P converted minus P friction and windage is going to be equal to P out. And again, this is all in watts. So now I have to divide this by 746 watts per horsepower to get that value. And lastly, excuse me, the motor efficiency is equal to P out over P in. Make sure you're doing these in watts. And so your P out is from part C. So P from part C divided by P in, which is the square root of 3 V line, I line times your cosine of theta or your power factor. I don't think I put the cosine of theta here. Apologize for that. And so I say cosine of theta, but that's just recognize that the cosine of theta is the same thing as power factor. And that's it for number 2. Question on number 2.
I think I'm good on number 2, Paul.
Okay.
Hold on, Paul. Hold on. I have a question about part A.
Sure.
So to get P air gap, I'm looking at 326, and you said P stator copper losses minus P core, and I'm looking at the presentation right now, and it says plus P core.
Oh, that might be. Are you sure I didn't go backwards? Because had I gone P air gap plus P core plus P stator copper loss, that would be P in.
Well, no, I'm saying you're doing, so I'm saying it's P air gap. The equation is P in minus P stator copper losses plus P core.
What slide is that? Because that's definitely a typo.
It's on 326, 16 through 30. And that's what I had on my note sheet as well. So I know I got that one wrong, but I wrote down the
What did you say the
formula
number
that I
was?
saw. Huh?
What
was that?
What page number was it?
10.
No, but you said it was pages 31 to 43.
16 to 30.
16 to 30. Just bear with me while it comes up. That's at page 10. Okay. So can I share that screen? Tell me when you can see
Yep, I can see it, Paul.
the PowerPoint.
Yep.
Good. So you're is this the correct slide?
Yes, this is the correct slide.
Well, there's a parentheses around here, correct?
Yes, correct.
So it's P stator copper loss plus P core, but that's the parentheses. So you put the minus, you distribute the minus amongst both of them, correct? See, the negative applies to what's inside the parentheses. So you would add these two together and then subtract the sum of those from P in.
Yes, and that's what I did, but it looks like you're saying you're subtracting all of them in the explanation that you just did.
That's correct, though, right? I mean, let me see if I can move this over here. If I just distribute this, this is equal to Pn minus P stator copper loss minus P core, correct?
Yeah, I guess so.
Yeah, I guess Paul, you might not be sharing the right screen.
Yeah, I think you're
Oh,
sharing
let me
the
share the other screen.
bode plots right now.
Sorry about that.
It's okay.
Can you see it now? What I just
Yep.
wrote? So that's, I think that's what I did here in this, right? It's
Yeah.
Pn minus P stator copper loss minus P core. Isn't that the same as this?
Sure.
Are you sure? I'm not trying, I'm just trying to understand if I'm understanding you correctly, I guess. And
No, you are, but I just don't understand how I guess I just don't understand that. So I guess I can just ask you after class.
well, it's okay. I mean, it's a good one to discuss. So unless I made a mistake, I think that equation is correctly. You can also just look at this figure here, right? And so moving from left to right, this is power going out. So you start off with this full input power. Now you take off your stator copper loss. Then the next loss you have to take out is your core loss. And at this point, all this power is available to jump from the stator to the rotor. So that's why it jumps across the air gap. And that's that PAG that we have. So to get to PAG, it's just this input power minus the stator copper loss minus the core loss.
All right. Yeah, I think I understand what you mean now.
Okay.
It's you're putting you're technically subtracting everything. You're just adding short stator copper losses in the core and then subtracting it as it's just like a different way of doing it. Is that kind of what it is?
So I can factor the -1 here, and I can
Yeah.
do this, right?
Yeah.
It's the same
Okay.
equation. I
Yep.
think that's what you're asking.
Yeah, no, sorry, I was just confused by that. My bad.
Yeah, okay. Anybody else not following process for that one?
I think I'm all good with it, thanks.
Okay. Anybody else? Are we happy with number 2? This one, this whole problem was pretty much based on just doing this diagram. If you had this power flow diagram and you understood it, you could just, take the errors, the power losses out, and then you could do the calculations that way, hopefully. Shall we proceed?
Yeah, you can go ahead.
Okay, thank you. All right, so a problem with some circuit parameters. The very first thing I'm going to do, let's draw my circuit. So I can see here that I don't have any core losses, R sub C. So I'm just going to put that here. So this is R1. This is, oh, it's not R2, it's JX1. JX1, JXM, and everything has been reflected onto the primary side. So I have JX2. Then it just depends on how you want to do this. I always find it to be useful to break these terms up. This is R2. And this is R2 times 1 minus S over S. But recognizing that the combination of these two is simply R2 over S, right? Because it does simplify your equation. Okay, so the first part of the problem is, let's go ahead and calculate the speed of rotation. So we know it's a 4-pole machine. And we have 60 hertz, so we have enough information to go ahead and calculate that. So N sub S is equal to, this is my synchronous speed, 120 times my frequency over the number of poles. That should be equal to 1800 RPM. So my N sub M is equal to N sub S times 1 minus S. Okay, I think I got 1740. Now, it's totally up to you to do the stator current, and I perfectly gave you credit on this approach. You could have certainly done circuit analysis to do the equivalent. What I did is I did the loop equations, and I said I1, I2 is equal to, let's see if I can do this quickly. R1 plus J times X1 plus XM minus JXM. It's a symmetrical matrix, so JXM. And then this one becomes R2 over S plus J times X2 plus XM. That's inverted, and then that's multiplied by, so here's what I got to be careful. This is a 40 volt machine. Y connected, we're going to assume. So this is over the square root of 3 at an angle of 0. So my voltage is 480 over the square root of 3, angle of 0, and there's no voltage here. And all you needed to do was pull out what I1 is equal to. I1 has a magnitude and an angle. Oops, let's see if there's a question here. Yes, of course. So I1 is equal to what I calculated when I did this way. I just pulled it out is, let's see, what did I write down? 116 at an angle of minus 26. Ballpark, again, it depends if you used the equivalent circuit approach, you know, the Z Thevenin, or if you did the exact approach, either one. So that's that first part, that's the stator current. The next part is what's the power factor? It's just the cosine, because the angle of the voltage is 0. It's just the cosine of 26. So cosine of 26, and don't forget it's negative. So you needed to add the fact that it's lagging, because the cosine of positive 26 is the same as the cosine of negative 26. So if you didn't do that, you know, power factor has two parts. It has a magnitude and a direction. And the direction we do is either leading or lagging. So this one is, again, so it depends a little bit about which way you did it. Because I had I1 and I2, I knew what my rotor current was. So the current actually going through the rotor. So all I needed to do was find P developed, which again is that equivalent mechanical power or the power that you get because of this resistor over here. So P developed is going to be the magnitude of I2 squared times R2 times 1 minus S over S. That's a single phase. I've got 3 phases, so I multiply that by 3. That's my developed torque, my developed power. My output power, so if I remember my diagram, here's Pn, and I've got all my power losses. This is the stator copper loss here. This is rotor copper loss here. So when I did my circuit analysis, I've already taken those powers out. I can calculate those directly. But what I ended up doing was I knew what P developed was, which is the torque, which was the power over here. The only power now that I need to remove is any rotational losses, any friction windage. So P out is equal to P developed minus P rotation. Okay. And again, you were absolutely welcome to do whatever technique you wanted, but the reason why I like doing this I1, I2 approach in a matrix is because I can immediately calculate what this current is because I have I2. If I don't have I2, now I'm going to have to do additional circuit analysis to take out rotor copper losses. Actually, I would have only had to take out rotor copper losses. So you could have just done, you know, the PN minus the stator copper losses and minus the rotor copper losses, but I just find it to be more efficient to go directly and pull that out from here and get P developed. Okay. That was probably the hardest part of this one, in my opinion, was figuring out the current to use and then calculating it over here. So once you have that P developed, divided by omega sub m is equal to torque developed, and P out divided by omega sub m is equal to T out. My efficiency is P out over P in. max torque about developed. So this is where it was up to you, but if you did the script in MATLAB, you could have certainly just pulled it off the graph. But I'm assuming most of you all did the V Thevenin approach. So V Thevenin is equal to your input voltage, V phase, times XM over the square root of R1 squared plus X1 plus XM, that quantity squared. That gives me V Thevenin. Once I have that, then I can get R Thevenin, which is equal to R1 times XM over X1 plus XM. Again, this is an approximation. And then once I have that, then I can go ahead and solve for my T max. So T max is equal to 3 V Thevenin squared over 2 omega sub S times R Thevenin plus the square root of, oh, sorry about that, R Thevenin squared plus X Thevenin plus X2 squared. And when you did the T max calculation, I think I got 11, 12, around 1200 Newton meters. Okay. So that was just plugging and checking the equation. But again, you were certainly welcome if you wanted to use the MATLAB plot. Just say, instead of using this approximation, I did this code and I wrote this code and I did these 10,000 calculations or whatever you want. And then reading off the plot gave me torque max of 40. Last one, which is my starting torque. So my starting torque was equal to 3 times V Thevenin squared, R Thevenin, all over omega S, times R Thevenin plus R2, that quantity squared, plus X Thevenin plus X2, that quantity squared. When you did that, you had around 500 meters. And that was the test. Questions? See if I can see anybody's smiling face. Please get their cameras off. So what did everybody think of the test? Too hard, too easy, just right?
I liked it. It was good.
Okay, no surprises, no tricks, everything that we've been covering and familiar with. Because the average was quite a bit higher in this test than the previous two. So it seemed like either the repetition of doing this is finally getting familiar with us, or because of the structure of the test, but you kind of have to do this with these induction motor parameters. Like, it doesn't seem fair to me to just say, give me what the maximum torque developed is on this particular problem, because there's a lot of other things that have to happen, which would make it, I think, more difficult to do this problem. So that's why there's so many parts and steps to tackling this problem. Any comments or questions? All right, well, as promised, I'm just going to go through the exam. If anybody has questions, I'll be available during office hours. Yeah, if people want to meet with me individually, I can always set up waiting rooms. So if people want to talk specifically, then we can go ahead and talk right during the class if you don't want to wait around. But like I said, I can speak privately to people with waiting rooms and go from there. So unless there's any other comments, have a wonderful day, and I will stop the recording now, but I will keep the class on and go from there. So thanks, everyone. Take care.
Paul,
Okay, you too.
unrelated to this test, but for the final, are we also allowed a note sheet for that?
you can have 4 note sheets, one for
Four
each
note sheets.
test, one for each test, as well as for the final. If you remember when people were asking me about the test, you could bring your formula sheet, and everybody asked me if I wanted it. I said, no, you should keep it. And the reason why I should keep it is because if you put all that time developing it, you can just bring that for the final. So hopefully nobody's pitched their sheets, but obviously you can still create one more sheets.
Thank you.
Sure. Anything else from anybody?
Yeah, hey Paul. I think
Yes.
Mac and I we're just gonna ask if we could go over our contract for
Yes, if you
350.
want to stay on, I can set up a private meeting, a group meeting with yours, but I'll probably have to do one of the other students first. So if you just
Okay.
wait in the class, we can go from there.
Yeah, sounds good.
Okay, so I'll stop the recording.